Hello, my name is Michael Glinsky, and I'm going to be talking to you today about the relationship of the Mallat Scattering Transformation, some relatively new mathematics, a deep convolutional network, to causal physics and complexity. You can find the content of this presentation in the SAND report available on the archive at the link that is shown here. This work was done by myself in conjunction with two postdocs, Thomas Moore and Will Lewis, and two other staff members, Matt Weiss and Chris Jennings, at Sandia National Laboratories. Also, very significant counsel and advice was given by Stefan Mallat, and during two different stays that I had for 3 weeks and visits to him at Collège de France in France, in Paris. Also, Ben Lascock and Brendan Hall were the system architects, the software architects, and the programmers that implemented the Mallat Scattering Transformation within the Keras TensorFlow environment. And I'll talk to you more about that at the end. This is really the summation of what the talk is, and I'll get back to this slide and review it again at the end. But it gives the connection of the Mallat Scattering Transformation to causal dynamics, both from a classical as well as quantum field theory viewpoint, and also to machine and deep learning through its connection to convolutional networks. That this transformation is useful for machine and deep learning of causal physics. It's also an important tool for theoretical physics in the analysis of turbulent emergence behavior, self-organization, and renormalization. Examples of this, as well as how it can be used as a tool, will be demonstrated throughout the talk. The thing that you do want to remember, and in the end, is that this Mallat scattering transformation is a iterative, multi-scale, hierarchical transformation based on the Wavelet transformation. The first order and the second order are shown here. That the first order is a function of 1p or inverse scale. I will show that this can also be a canonical momentum, an action, an energy, or quantum numbers of the system. That it will also be shown that this is a convolution of a signal with a bank of mother wavelets or filters of different dilations or scales that are 1 over p. Then there is a nonlinear rectifier, which is the absolute value applied to it. And finally, a father wavelet or a windowing function. You can also take a look at this as a localized Fourier transform with a patch function, which is the father wavelet, and then a matched mother wavelet that goes and takes the amplitude of it. This is the modulus, and I'll comment on the phase in just a second. The second order Mallat scattering transformation is a function of two p-values, or canonical momentums, that you start with the one convolution of the signal with the mother wavelet and the modulus nonlinear rectifier, but before you convolve it with the father wavelet, you end up convolving it with a second wavelet, since the wavelet transformation still has a time dependence in it. You can do this. If it's a Fourier transform, you could not, because it doesn't have that time dependence. Rectify it again, and then convolve it with the father wavelet. This can be gone and continued to higher order, I'll talk about why that isn't useful in just a second. But this also can go and be related to classical kinetics and also quantum field theory in the following ways. It will be shown from the classical kinetic viewpoint that if you now go and take the look at and derive the master equation, which is an expression for the change in the one particle distribution function, which is going to be whatever source term you have, plus the two particle distribution of p prime p minus the two particle distribution function of p prime. And these bars mean that they end up being an average, which will be explained a bit later. This also, through this definition of a reaction rate being the two particle distribution function or correlation function divided by the one particle correlation function, you now see that this ends up being what I end up saying probability in from all states p prime minus probability out of state p to all state p prime. That's demonstrated here on this diagram, and you can see that the probability into it from all states p prime into p is going to be the amount of probability or the distribution function in the state f times the rate at which you're going from p prime to p minus the probability in the state p times the rate that we're going from p to p prime. The interesting thing that will be shown by a modified version of the Wigner-Weil transformation is that this f1 bar of p is nothing more and can be shown to be equal to this convolution of the defining the Mallat Scattering Transformation. And the two particle or correlation function or distribution is nothing more than what has already been shown to be the definition of the second order Mallat Scattering Transformation. Now, if we continue on to the field theoretical viewpoint, that we are going to also show that the S matrix, or the generalized Green's function of a scattering cross-section of n particles into m particles, or n fields into m fields, is also related to the nth order scattering coefficients. And that's what ends up being shown here, is that the first order or Green's function or S matrix is the first order Mallat scattering coefficients, and the same holds true for the second order S matrix of one particle in, one particle out is also that. But it will be further shown by some manipulation and evaluation that you can identify the first order Mallat scattering transformation as the classical action averaged over quantum fluctuations, and the second order is nothing more than the 1 over the renormalization mass as a function of the initial and the final scale of the interaction. And in terms of a Feynman diagram, you see that a particle of mass m is mediating this interaction, is scattering a field of action phi naught of p into a field of action phi naught of p prime, and is again this particle of this mass which is doing the scattering. There also ends up being a phase associated with this, There's also a massless gauge boson associated with that, which will scatter this without any change of energy into or change or injection of action from one phase to another in this case. Also, you can say, why do we stop at second order? Well, practically fine, there's very little sort of action, pardon the pun, in terms of higher order in a practical viewpoint, but also there is the statistical realizability theorem that either you have to stop at second order or you have to continue to infinite order, which means that there really is infinite information in the signal. Since there is finite information in the signal, this needs to be truncated or needs to stop or will stop at second order for the cases we're dealing with. But another way to go and take a look at this is that the first order Mallat scattering transformation is giving you information on the state of the system, the F of the system, or the action of the system, where the second order is telling you what the kinetics or the transition rates are from one state to another, or these reaction rates, which will be F2 divided by F1 bar, or it is the mass that is scattering one state into another. Well, you really know everything about the talk and everything that I'm going to be saying now, and sort of why this ends up being so important. Because what it really does is exposes both the state of the system and also the transition rates to machine learning. And also you can see that this goes and has the form of a convolutional network, but both the rectifying function as well as the coefficients end up being predetermined here so that there is much less to learn. And also, if you want to know how to evolve the first order scattering coefficients, by reference to this master equation, it ends up being a simple linear, can be derived to be a simple linear relationship associated with the F2s over F1s. Okay, what are the practical applications of this? First of all is a deep representation for machine and deep learning of these causal physical systems that can be used directly for classification or characterization or identification of these systems. It can be used for regression. It can be used for surrogate construction of causal physical system evolution from an ensemble of states that sampled these transition kernels and the current state, which will also be sampled. More explicitly calculated. It can also be used in a much more straightforward way as a metric of image morphology or complexity or texture. This can then be used to directly compare simulations to experimental images and can be used to compare experimental images to other experimental images. It can also be used to estimate the parameters of images with uncertainty by a shallow linear regression, as will be shown. Also, it's a very good space in order to be doing a sophisticated background subtraction. But really, if you step back, is that the real problem with complexity is the fact that you don't have a metric. You need a metric on the space to make any progress. And this is giving you that metric in order to be able to analyze complexity and emergent behavior. Okay, here is the roadmap of the talk. First of all, I'll give you an introduction to the Mallat a simple pedagogical explanation to the Mallat scattering transformation as a deep convolutional network with predetermined weights. I'll then go and show you the details of how we get the relationship of the Mallat Scattering Transformation and the understanding of it from a classical perspective as a manifold state Wigner-Weyl transform of the density operator. This is a bi-transformation because operators have inputs and outputs, and you have to transform each side of it. And also that it ends up being on a manifold with a spherical or SN topology, you now can use a periodic Fourier kernel, and that reduces to the bispectral transformation, which is used in order to do machine learning associated with density functional theory calculations. And then finally, I'll go and show its relationship to the generalized master equation, or the relationship of the F2 to the evolution of the F1. I'll move on to the quantum field theory perspective, where I'll show the relationship to the generalized Green's functions or S matrix and how that comes about, and then do a further simplification in the relationship to a Feynman diagram where the first order is related, Mallat scattering transformation is related to the quantum fluctuations, averaged classical action, and the second order Mallat scattering transformation is very simply related to the renormalized mass as a function of initial and final scale. Finally, I'll get to applications of this in terms of image or texture classification and identification. Go and show ways that it was used as a metric to experimental to computer simulations. As part of this, we needed to develop an advanced background subtraction. Next, I'll go and show an example of a parametric model estimation of experimental images with uncertainty estimation via regression. And finally, I'll have comments on some future directions in the use of this in terms of machine and deep learning of causal physics for making surrogates of PDEs or kinetic evolution, and causal analysis, that is, what are the PDEs, that is, the physics that we should be using. And finally, I'll go and talk about the identification and characterization of emergent behavior and why this is especially good at doing that. Now let me start off with introducing the Mallat scattering transformation by talking real quickly about what is a wavelet transformation and some of the deficiencies of that in a Fourier transformation that were remedied by this construction. First of all, the wavelet transformation is a convolution of a signal with a bank of filters that are formed from a mother wavelet via dilations and translations according to a convolution. And the convolution ends up giving you signals with different frequency content and subsequently more band passing or more restricted band pass. Here is an animation of a convolution of three different wavelets, small, medium, and large, with this blue signal. You see that we have the convolution with the smallest. Here we're working on the ones with the medium, and finally with the large wavelet. But what is sort of the good, the bad, and ugly of both the Fourier transform as well as the wavelet transform? We're going to look at it in terms of its continuity to deformation, or its Lifshitz continuity, and its stationarity or invariance to translation. As you can see, when we have an example signal and we end up having a small continuous deformation of that. For the Fourier transform, you can see that this small deformation leads to very large changes at small scale to the Fourier transformation. And in fact, this is related to the reason for the ultraviolet divergence in renormalization theory that is the plague of renormalization, and in fact why you have to have the renormalization in order to remove or divide out those divergences. Where the wavelet transform is Lifshitz continuous, you can see there is a small change or deformation in the wavelet transformation for the small deformation in the original signal. Where with respect to translation, it's just the opposite, that the Fourier transformation is invariant with respect to translation, where because of the resulting or residual time dependence in the wavelet transformation, it is not. So that they're sort of complementary in what they're good at and what they're bad at, being the Fourier and the wavelet transformation. Well, that the way that we go and that Stefan proposed resolving this is to use the sort of disadvantage, the lack of stationarity of the wavelet transform or the time dependence as its sort of solution. And that if we now go and take a wavelet transformation, because we still have time dependence in that, we can take the wavelet transformation of a wavelet transformation. But we have to make sure that we haven't already filtered out those frequencies that we're going to be taking the subsequent wavelet transformation of, that for the medium one, we can only take it with the large, and for the small, we can take that with both the medium and the large scale. You can do that one more time for this one. You can take the one with the medium and then go and transform with the large, so that and you can now go and see there's this binomial distribution, and for only having 3 different sizes, you can only go to third order. But if you now go and have more sizes, you can go to higher order according to this binomial structure. But we still need to go and take this father wavelet, and every mother wavelet there's a father wavelet. It ends up being an effective windowing function, so that now we can go and take and apply this windowing function to the rectified transformations, wavelet transformations, that will go and give us numbers and turn it on the side. And what we get for the first order is effectively an optimized windowed Fourier transform that now ends up being deformationally continuous, as well as approximately translationally invariant, just so the translation is small compared to the span of the father wavelet. Let me talk a little bit about the way this goes and get displayed in 2D. And you can see here that as a 2D Fourier transform, it not only has magnitude, but it also has orientation. For the first order transformation, we can go and post the value of the transformation. That's a function of the p-value and the sector associated with that p-value. Because of this scale ordering, that the second scale needs to be smaller than the first scale, that you end up going and finding that you now can go and post the second one inside of the quadrant of the first one. And you can now go and sort of sum these up because of these scale orderings of small to large that you end up having. And that so that you now can also post the second and third order on one of these sector plots. In fact, you can sum them, but for clarity, we'll go and keep these separate. Shown here on the left is one of the images that we're going to be looking to analyze. And that one thing that you need to decide upon is the patch. And you want to make sure that the statistics are really stationary over the patch or slowly varying, or that the dynamics has sort of a dynamical scale length that ends up being smaller than the patch size that you're dealing with, or the wavelength of the waves end up being smaller than what those patch sizes are. And because all the action for us ended up only being in these 4 quadrants, that you'll see that in some of the displays we only show 4 out of the 16 quadrants. But now let me get to the explanation, or the physical explanation from the sort of classical perspective. And one thing to note is all of our systems are diffeomorphisms, whether or not those are kinetic equations, whether or not those are fluid equations, whether or not those are field equations. And here I use the notation of exterior calculus so that it will be manifold, sort of safe or relevant. And that you'll see the reason for that in a bit. And here I'll start with the generalized Liouville equation on the manifold, which shows you the evolution of the form, covariant form rho, which can be either a statistical distribution function or a quantum mechanical, quantum field theory state, or quantum mechanical state, and that you end up seeing that the full derivative of that equals 0 underneath a flow by a normal sort of variant vector field, and so that you see where this is the Lie derivative of the form by the vector field. We now can go and integrate this over all but little n particles, and we now see we have this full Lie derivative is equal to a Lie derivative of an interaction field with the n+1 particle form. And also note that these Lie derivatives are going to be things like a commutator of operators, a Poisson bracket. There'll be things like v dot grad v, or an acceleration dot grad associate onto things like a normal function in terms of configuration space. But you start now seeing why deformational continuity is so important, this Lifshitz continuity, since all of these physical systems go and involve a diffeomorphism, deformation, or advection. And now let me go and also introduce these bar functions and get to a generalized master equation, invoking the statistical ideas of Bogoliubov. First, we need to pull back the 1 particle and 2 particle BBGKY hierarchy. And you now go and see what you end up getting here are these Poisson brackets in place of the Lie derivatives, and you end up seeing the first vestige of the collision operator appearing over here, and then also an analogous equation at second order. We now go and invoke the idea of Bogoliubov that the F1 relaxes at dynamic rate, or the circulation rate, or kind of the wave frequency, to an average value. It gets mixed along that dynamic sort of closed orbit or path if you have those. And then the F1 evolves on the collisional rate, which ends up being much smaller than this dynamical rate. F2 then relaxes on this same collisional rate, and then it evolves on the correlation rate, which ends up being much smaller than the collision rate. And then the next thing is that underneath these conditions, we can either reduce this to a Boltzmann equation, but I find that it's much more useful to go to its cousin, which is a generalized master equation, where we now go and see that the change in this average one particle distribution or state, quantum field state, ends up being the difference in the two-particle distribution function, where again we can make this identification of the reaction rate as being the quotient of F2 bar over F1 bar. And so that we now go and get to this definition and perspective that I talked about on the previous slide. But there's still one very important technical detail, which is to go and figure out what this F1 bar is. In order to do that, we're going to dust off some rather old mathematics coming from 1927, the Wigner-Weil transformation. And what Wigner and Weil were wanting to do in these early days of quantum mechanics was to go and to transform operators into functions on phase space. And they did this by doing a bi-Fourier transform. Again, you need to do this because operators have both an input and an output side, and then you ended up going and having two Fourier kernels in this definition. Well, they ran into a load of trouble, and they ran into the load of trouble because of the Fourier kernel. This only is going to be valid if you're dealing on Sn or a periodic spherical topology, and it doesn't work if you end up going on to a general manifold of arbitrary topology. And what we've gone and have proposed is now to get a manifold safe Wigner-Weil transformation where the Fourier kernel is replaced by a mother wavelet, and you'll see that an expected value averaging we end up doing by introducing it in terms of the father wavelet. But it also ends up being necessary because you need a partition of unity, and the father wavelet is a very convenient and properly defined partition of unity. What is a partition of unity? It's a patch function, like you can see that I sort of showed you with respect to the definition of how we did this sort of localized Fourier transform over patches for the 2 dimensions. And you now need to divide up in this case, a torus, a non-spherical topology, in terms of these patches associated with these sort of different father wavelet functions, and then you can go and proceed on. Well, if we now go and look at this modified Wigner function, which is the Wigner-Weil transform of the density operator, or the state operator bra-ket F, that lo and behold, you end up finding that ends up being the modulus squared of the transformation. Since we're interested in F, not F squared, we now need to go and take the square root of it. We also are interested in the expectation or the average of it. And so that we naturally now come up with this is the definition of what the first order Mallat scattering coefficient is associated with what the F1 bar is. And also if we now go to the two-particle correlation function, the F hat, and what the expectation value is of the Wigner-Weil transform of that, it ends up, can be shown to be exactly the definition of the second order Mallat scattering coefficient. This is the Mayer cluster expansion on the manifold, the pullback of it. Now let's turn our attention to quantum field theory. Let's start with the Lagrangian perspective of the using the normal generating function, which is a function of the field, but now I'll explicitly put that in the P transform basis, and then you end up adding on this generating current function, so that if you want to now go and do a functional Taylor expansion of this Z functional of J, that you end up finding that and can go through some derivation and show that's nothing more that this will be the scale ordered product of these correlation operators F, and that also through an evaluation of stationary phase of these Gaussian integrals, that you also end up finding that you end up getting these, but the stationary phase removes the phase from this and naturally leads to the definition of these absolute value signs in this case, and gets to the exact form of what the nth order Mallat scattering coefficients are. It's also known that these are the scattering cross sections or the generalized Green's functions of the system. There needs to be some sort of extra sort of truncations and manipulations in terms of a prefactor. But up to these prefactors, they're the S matrix of the system that tells you the scattering cross section of N particles into M particles. But now to go and to sort of understand this in terms of the first and second order, in terms of things which are more tangible, we define the effective action through the normal Legendre transformation of the action, expand that in S and phi, and it can be shown then that the first order Mallat scattering coefficient is nothing more than the classical action averaged over quantum fluctuations as a function of the inverse renormalization scale. And the second order is nothing more than the two-state scattering cross-section, or the scale-dependent, in terms of the initial and final scale-dependent renormalized mass of the system. And in a Feynman diagram sense, that you end up scattering a field with momentum p and action phi naught of p into a field with action phi naught of p prime, and that's mediated by a particle or of the field with mass p and p prime as defined here. And you also can think of this as sort of the 1 over mass gives you kind of the frequency of this, or the sort of energy that ends up being sort of imparted into the particle as you go and have that scattered. What was the physical inspiration for us to do this? At Sandia National Laboratory on our Z machine, we have been going and doing these implosions of deuterium plasmas that are initially at about 1 milligram per cc, and we compress them up to densities that get close to solid densities, about a quarter gram per cc, and in the process we heat that up to about 2 to 3 kilovolts, so that it becomes a thermonuclear burning plasma that goes and has a large amount of X-ray radiation, which we can image, self-emission, X-ray emission, and that, as you see here, over many different cases, we always get these DNA-like double helical structures associated with it. What's kind of amazing is that we've gone over about 6 E-foldings of the sort of, in terms of a linear instability time. And also we've been able to go and compress, and again these plasmas here you can go and see are about 1 centimeter high and about 100 microns in diameter. But if you go and take a look at the detail of the diameter of these threads, they get to be less than 23 microns in size, which leads to convergence ratios of 40 at the 120 microns, but at the 23 microns, those are convergence ratios that are greater than 200. This was really surprising. In the laser implosions at the super laser at Livermore, they want to get high convergence ratios, but are hard-pressed to get convergence ratios of 20. And we didn't expect to be able to converge these by more than a convergence ratio of 10, but we've been able to get more than 20 times that. And also what goes and is indicated of a self-organization is the fact that, other than the fact that just the fact we're getting these structures of this form, is that also there is a threshold in magnetic field below which you get no organization, and you end up getting these things to not have a very well-formed helical form with very large aspect ratios between the overall compression of this, because this is originally a centimeter in size, and the final form of this is 23 microns in size. So we're definitely getting an inverse cascade here and a self-organization. And we want to go and be able to study and characterize this. So we started by constructing a synthetic model and testing out and designing and demonstrating that this ends up being a valid metric to tell the difference between these synthetic models. That we ended up having about 11 different thetas that determine the overall structure, and then we had stochastic parameters that went and determined things like the background noise, the amplitude of the signal, and sort of arbitrary phase shifts in the helical structure. This goes and shows the ensemble. We went and had a base class, and then went and had both a range, a modest range of the theta parameters and a larger range of the stochastic parameters. And then we ended up going and having different classes where we significantly changed one of the theta parameters and repeated that thing in order to be able to get an ensemble. And you can go here, and we've gone through 3 of the classes. But now I'll just go and see that and show you kind of the base class associated with each of the 11 samples. And you can see by going from class 1, which is the base class, to class 2, that we took theta 1, and that class 2 is shown up over here. And you can see that the precision will be the size of each one of these sort of clusters, and the separation will be the distance between them. And that in the transform space, using the Mallat Scattering Transformation as a metric, that the precision ended up being about 10 to the minus 4. The separation of these classes ended up being 10, or that the separation was 10 times the size of the clusters. The probability of incorrect classification when done in a standard way on a test data set ended up being 0%. And utilizing the separation matrix to give us some more resolution on sort of a confusion matrix, you can go and see this is roughly diagonal with very small sort of off-diagonal elements on the confusion matrix. We then went and used this metric to be able to tell the difference between, or similarity between, experimental images and computer simulations. One thing to note, these 3D simulations are large multi-physics simulations that take about a week on clusters that have about 5,000 cores on them. And we ended up making synthetic X-ray self-emission images that were driven by liners, beryllium liners, of different thicknesses or aspect ratios, which are length to thicknesses, and that the thickness ends up getting smaller as we move to the right. And we ended up having experiments that were supposed to correspond to our simulations. But we want to ask the questions of, do the simulations look like the corresponding experiments, and which experiments are the experiments significantly different in their character? Well, we wanted to go and use this as a metric, but we ended up finding that there was a problem, was that there was a systematic difference between all of the simulations and data. And you can see that here, that there ended up being these divots in the data, and this was dominating everything, any differences or similarities in the simulations to the data, indicated by precisions that were only about a half, and separations of the different aspect ratios of about 2, which really did not make it effective. Well, we ended up coming up with a way to subtract out this background, but in the Mallat Scattering Transformation space, by taking the first principal component of the simulated today's data covariance and then projecting that out, removing this divot that was in the data and was not in the simulation. And once we did that, we ended up increasing the precision down to about 1/10 and increasing the separation up to about 5. Once we did that, we ended up finding that the metric then will quantify the similarities between the simulations and experiments, which will enable us to use these images in an uncertainty quantification and verification, and it also allows for quantified statements to be made about the morphology or the self-organized structure. For example, here we can state that the simulations correspond to the matching experiments. The simulation of the 4.5 aspect ratio is most similar to the data of the 4.5 aspect ratio. The simulation of the aspect ratio 6 is most similar to the data of the aspect ratio 6, and that the simulation of the aspect ratio 9 is most similar to the data of the aspect ratio 9. But there is similarity of the AR9 data to the AR5 simulation. Now let's move on to exactly what is it about those images that are different. To do that, we ended up making a regression of the thetas to the scattering coefficients. So we ended up forming an ensemble of the synthetic images over the theta variation that we sort of expect in the experimental and simulation images. We form up the scattering coefficient, and then we ended up forming a linear regression in terms of the singular value decomposition of the scattering coefficients and the theta values. And then, so that given one of these experimental diagnostic images, we can give this regression to give us estimates of what the theta parameters are with respect and their uncertainties, and also can go and show you what the quantified synthetic looks like, along with an ensemble of what we think the uncertainty is of that. This goes and shows the ensemble that we used to form the regression, and then what we did was form the regression, took the scattering coefficients of a test data set, and that then applied the regression to it. And what is displayed here on the right is a reconstruction with an arbitrary phase of the of using the most likely theta parameters. You can see that it's fairly remarkable that what we end up having on the right up to a phase really looks like what is on the left. But also to go and take a little bit closer look at that, what you ended up seeing here is the predicted theta versus the actual theta in the training set. And you can go and see that there are very tight to modestly tight linear relationships between the two, and also that the correlation coefficients of these, even though that they are not in the SVD space, end up being extremely diagonal with some modest correlation, let's say, of these two, number 9 and number 10. This goes and shows the application of this to one experimental image. You can go and see the estimated theta values along with their asymmetric uncertainty range, asymmetric because it would be symmetric in the logarithm, but it's not symmetric in the exponential of that logarithm, or the original theta value. You also see here on the right the ensemble of the prediction associated with these uncertainties. So we sample from these thetas with also including the cross correlation, and then go, which is not very great as you saw before, and then go and show what the predicted ended up looking at like, and also having to add on some of those random phases in order to reconstruct it of the zeta values. This now goes and allow us to go and do two different shots. One is a coded liner, dielectric coded, another is not. There are also different aspect ratio. Here, if you look at the images, you can see that they qualitatively look different. They have very dramatically different Mallat scattering transformations. By using these regressions, we can estimate the different theta values with their uncertainties. And you can see that some of these parameters are really the same to within the estimated uncertainties. Other ones are sort of marginally separated, where other ones have a very significant difference in them. And now let me turn to really why these metrics are very good and are directly related, and how they're directly related to the self-organization or emergent behavior. Let me start with the generalized master equation. And remember, that's the junk in minus junk out integrated equation. Normally, in terms of linear instability analysis, that you expand the F1 in terms of a small perturbation, you end up getting an expression or a dispersion relation, which you solve for these p-values, and that you end up finding that these p-values end up having an oscillation component, but they sometimes have a unstable imaginary component, and that all of the analysis goes around whether or not they do or are unstable, and if they are unstable, what is their maximum sort of instability or growth rate. Well, since we have many e-foldings or generations that we're well beyond this linear instability analysis, and we're more interested in the nonlinear steady state that these systems will evolve to, that ends up being time dependent, and is going to be, and you can do that by setting the partial derivative with respect to time to 0, and finding that this steady state is going to be a fixed point of the transition kernel, or kind of the two-particle distribution function of the system. And that then you can go and find that this steady state that you end up going to for sort of normal three-dimensional turbulence, as we would call it, that you'll find that this steady state ends up, if you're driving it here where this little red bump is, that will cascade to smaller scale, eventually reaching a Kolmogorov scaling at steady state and then being dissipated at small scale, or in terms of this jet, you'll see it goes and reaches this sort of well-developed turbulent behavior. But also there's another class of behavior where the opposite thing happens. 2D Navier-Stokes is that because it has a conserved circulation associated with it, or entropy, and that because of that you end up having a minimization of energy underneath that conservation, so that things want to go to large scale associated with that, and you'll go and see this inverse cascade or this self-organization into large scale structures. Our system is not 2D Navier-Stokes, it's 3D MHD, but the magnetic field in that case is giving you a conserved helicity or helical winding, and that's why we end up seeing, instead of these things going into vortexes, that they end up going into helical structures. And here is an example of that through a related experiment at the University of Michigan. And you now can go and see the evolution of this liner where small perturbations go to large. That's explicitly shown here where this edge is now plotted at different times. And you can see and track this mode merger of small perturbations into large perturbations. You can go and see that that's evidenced by the dominant wavelength getting longer and finally saturating at these large states. And you can now go and also see that it's being pumped here at the small wavelength, but it goes to the steady state at the distribution at the longer scales. And so now what you can go and study is that, or the main questions you have is, what is this steady state? Well, that's the first order Mallat scattering transformation. That's a fixed point of the second order Mallat scattering coefficients. And you can go and see that this ends up being 1 at much larger scale, but it has this threshold because there's no limit on the size of the probability container for BZ equals 0 until you get to a finite threshold in BZ value, so that you will now go and see that for you to have this sort of finite container or structure, that you end up having to have a finite BZ. And then the second major question is, how does it get there? Well, that is the second order Mallat scattering coefficients that tell you how this is transported to this fixed point of the transition kernels. Finally, I wanted to go and mention that Nthought has put together an efficient professional implementation of the Mallat scattering transformation using Keras TensorFlow that implements both the 1 and 2D Mallat scattering transformation along with visualization to arbitrary order. That this implementation is compatible with efficient inversion of the transformation, since the derivatives or adjoints are defined through the Keras TensorFlow infrastructure. And also, since it is implemented in the time domain as a convolutional neural network, that allows a richer set of network structures that can be investigated in terms of the structure of this. And now finally, let me get back to the sort of summary slide, which is a connection of the MST to causal dynamics from both the classical and quantum theoretical physics point of view, as well as the machine and deep learning. And just concentrate down here, where the first order Mallat scattering transformation is the state of the system, that's related to the one particle distribution function of the classical state, classical kinetic state, or the classical action averaged over quantum fluctuations of the in terms of the Feynman diagram, or the one particle scattering cross section in terms of the S matrix or Green's function, where the second order Mallat scattering transformation is now has this convolutional structure, which you can see is kind of a second level deep convolutional neural network with predetermined weights. It's also related to the average two-particle correlation or distribution function, which can be then related directly to the transition rates of the system. From a Feynman diagram viewpoint, that is the mass of the particle that is mediating the field that's mediating the scattering of the field. It is also the two particle in, one out scattering cross section or S matrix of the field. And that's really it, and is the reason why that the first of all, you can look upon this as a convolutional neural network with sort of predetermined weights that you don't need to learn. And if you want to go and understand how the system evolves, that ends up being a very simple linear relationship of the master equation for the change in the first order scattering coefficients in terms of the second order scattering coefficients, where the weights are also predetermined. And that the research that I'm working with on the mirror is to go and take a look at, first of all, learn the deep convolutional neural network and whether or not it goes and displays the structure of this deep convolutional neural network. Another thing I didn't mention is that this is also unitary, which is what you need for the propagators of it, sort of by a construction, so that this ends up being unitary or having this specified structure. And second of all, when we go and try to evolve these systems, whether or not it's those perturbations that you saw before, or it's Berger's equations, or it is MHD equations, or it ends up being the, let's say, 2D Navier-Stokes, that that we'll go and derive what these coefficients are of the sort of the simple linear regressions, but we fully expect that to be what is predicted in terms of these very simple relationships given by the master equation here. And again, thank you very much for your attention.